Now, in the example which we discussed, we introduce another term called rotation. More formally, it is called rigid body rotation. Why is it rigid body rotation? The body as a whole rotates, which is something to similar to your rigid body mechanics which I have studied earlier. When the body rotates, there is no internal strain, stress, nothing, it just rotates, that is all. Okay. That is why it is called rigid body rotation, because the entire body rotates, there is no relative movement between any two points in the body, okay, which means there is no strain, there is normal strain, there is no shear strain, which means other way of putting it is the body does not undergo any deformation. When we say deformation, what did we say? Change in length, change in angle, no change in no deformation at all, which means that you need not worry about deformable bodies, it is just a rigid body, and that is why more formally called as rigid body rotation. Remember, some time back we said translation, that is also rigid body translation, the entire body just moves, just like I am moving like this, it is rigid body translation. If I rotate, that is a rigid body rotation. Okay. So, that is why it is called rigid body rotation. Now, we will have to relate this rigid body rotation to displacement field, and that is what we are going to do now. That is easy, because already we have got all the expressions at hand, a small sign has to be incorporated. Okay. Let us see how do we do that. Now, rotation of line segment PQ, moment you talk about rotation, remember some time back we talked about moment balance, immediately we chose an axis about which you would take a moment. Similarly, here you are talking about rotation. So, when I say rotation, what is the axis about which I talk about rotation? In this case, the plate lies in the xy plane. So, which means my axis of rotation is along the z axis. Okay. So, rotation of line segment PQ about the z axis. Okay. What is that? That is alpha, that is the rotation of line element PQ. How do you represent? How do you represent? The nomenclature used is omega, okay, and it is about z axis. So, subscript z for the line element PQ. So, the nomenclature for rotation is that omega and about z axis. So, z for the line element PQ, and that is equal to alpha, that is very clear, the rotation is alpha from the figure, and we have shown that alpha is given by dou uy by dou x. Remember, this rotation is also, the way in which I written is also a point form expression. We have related alpha to this as a point form, because we made delta x tending to 0, delta y tending to 0, q tending to p, r tending to p. So, this rotation also, how do you imagine? At a point, once again imagine a small line segment, and how much it rotates is given by dou uy by dou x. Okay. Now, let us focus on the line element PR, once again about z axis. Now, if you look at the rotation, PQ has rotated in the anticlockwise direction, but PR has rotated in the clockwise direction. When earlier we are interested only in the change in angle, so we did not assign any sense of rotation, we are interested in alpha plus beta, angle alone. But now, because we want to quantify rotation, we will have to assign a direction. As usual, anticlockwise is positive. So, there is no extra sign here, but now when we write the rotation of element PR, which rotates clockwise direction, because clockwise is negative, I add a negative sign. So, how do you represent once again rotation? Omega about z axis for the element PR is minus beta, given by, we have shown already beta as dou x by dou y. So, rotation of element PR is minus beta is equal to minus dou ux by dou y. Okay. We assigned sense of direction. Now, earlier we are interested only in the difference between PRQ and PR star Q star. So, we are interested only in alpha plus beta, we need not worry about sign, but now we have talked about rotation, how PQ rotates, how PR rotates. One rotates in clockwise, PR rotates in clockwise, PQ rotates anticlockwise. So, we start assigning signs. Now, when we defined shear strain, what did we say? We take two line elements, and then what is the change in angle. Similarly, now the definition of this rotation is that average rotation of the element is equal to average rotations of the two perpendicular line segments. Okay. What is that? We earlier for shear strain we considered two line segments, looked at the different change in angle between them from initial to final state. Now, we are looking at the average rotation of these two lines. How much did this rotate? How much did this rotate? What is the average value of these two? So, average rotation of the element for this element is equal to average of the rotations of the two perpendicular line segments. Earlier also we considered two perpendicular line segments and looked at the difference in angle, but now we are looking at the average of the rotation of these line segments from the initial state to the final state. Look at, take this rotation, take the other rotation, find the average. That is how we define rotation of the element. So, in terms of expressions, what do you do? Omega z. Now, I do not write PQ or PR because it is omega z for the whole two dimensional plane or for the plate, okay, is equal to half of omega z PQ rotation for PQ, omega z PR rotation for PR, just add them and divide by 2, that is average value. So, 1 by 2 of dou u y by dou x minus dou u x by dou y gives you the rotation for the element. When I say element, the two dimensional element. So, always you imagine two ways. Physically you can imagine as a plate or it is a region, two dimensional region inside a solid object, because it can vary from point to point. Okay. Now, in terms of notation, we had two subscripts for shear strain gamma x y, epsilon gamma x y, two subscripts. Now, to begin with we had epsilon x and we want to have two subscripts for normal strain also. So, we said epsilon x x. Okay. Now, similarly for rotation, the notation subscript is only 1 because it says rotation about the z axis. What is the alternate way? Rotation in the xy plane. So, that every term will have two subscripts. So, this tells you rotation in the xy plane, this tells you rotation about z axis, equivalent way is rotation in the xy plane. So, omega xy is equal to omega z. So, this is the nomenclature which we will use, of course, equal to the right hand side expression. So, as we have done for normal strain, shear strain, we have related the rotation, rigid body rotation in terms of the displacement gradients. Once again these two gradients are very well known, they are known to us, we have already seen, but the subtraction and division by 2 gives a physical significance, namely the rotation. Okay. So, let us summarize all of them and also write for other directions, that is this slide. Normal strain we discussed normal strain or derived normal strain for a line element along x axis. Similarly, you can write for y axis and z axis, line elements along y axis, z axis. Shear strain we consider two elements which are along x and y axis. Similarly, you can consider along y and z axis, z and x axis. So, gamma x y is equal to dou u y by dou x plus dou e x by dou y. Just symmetrically replace variables. Okay. Symmetrically replace variables. Of course, normal strain was very easy, x x was replaced by y y or x replaced with y, very simple. Okay. X replaced with y and then x replaced with y. What do you do here? Once again dou gamma x y is given by this expression. When you want to write gamma y z, you are replacing x with y and y with z. Similarly, on the right hand side also you will get the expression. Okay. Similarly, and the third expression also, dou in the denominator you had x here, that became y, y here, z here, okay, and y became z here, x became y, just symmetrically replace. Okay. And rotation finally omega x y is equal to half dou u y by dou x minus dou u x by dou y. Once again just symmetrically replace, you will get the rotation in the y z plane, rotation in the z x plane. And just want to mention one thing in terms of remembering, you always like to remember few expressions at least. In terms of remembering shear strain and rotation, better to remember in terms of the derivative dou by dou x. We know they are cross derivatives. Okay. If you have x in the denominator, you have y in uy in the numerator. So, in terms of remembering, this can be remembered anyway because it is plus sign, but remember this, you need to remember the order, the sequence is important. So, one way to easily remember is start with dou by dou x, then next is dou by dou y. Moment you write dou by dou x, you know that this should be uy. If it is y, you know this should be x. So, that way you will not make any mistake, and of course, once you know that shear strain, remember that is also followed in writing this way. Here also only dou by dou x is written first and dou by dou y is written second. Okay. So, both are analogous, only sign change is different. So, that you can easily remember the expression for rotation and shear strain. Of course, you have a half here. Okay. We have related normal strain, shear strain, rotation to the displacement gradients. Okay. Now, we look at another strain which I have not defined, we will define and also related to the displacement gradient. Okay. That is called the volumetric strain. Just like the normal strain tells about change in length, the shear strain tells about change in angle, rotation tells about rotation, volumetric strain tells about change in volume. In a 2D it will tell about change in area. Now, to derive expression for that or to relate these two, we will consider a cuboidal element. The volumetric strain is change in volume is original volume, similar to a normal strain. Now, so we will have to find expression for new volume, and then old volume is a cuboid, then you can find out expression for volumetric strain. Okay. Okay. So, for deriving that we will consider a cuboidal element as shown here, subjected to normal strain only. What does it mean? You have a cuboidal element and there is only change in length alone, it will be decrease, increase, whatever can happen, but there is no change in angle. So, that is what is shown here. This is the cuboidal element. So, cuboidal element, once again you can imagine a physical object like this, or it is a 3D space inside a solid object. So, delta x, delta y, delta z is the initial configuration, initial state, and delta that is represented by the continuous line. The dashed line represents the cuboid, still it remains a cuboid. Why is that? Because there is only normal strain. So, it still remains a cuboid. To begin with, it was a cuboid, and after, let us say, subjected to normal stresses and so on, only normal strain happens. That is why in the final state represented by the dashed line, it still remains a cuboid. The lengths are different. Let us see how do we find out the lengths. So, we are considering a cuboidal element of lengths delta x, delta y, delta z. The volume of element before deformation, just a cuboidal volume. So, multiply all the lengths delta x, delta y, delta z. Now, we have to find out the changed volume, the new volume, the volume in the final state. How do we find out? It remains a cuboid. So, if we find out the lengths, we multiply all the lengths of each of the side. The length of the side before deformation is delta x. Now, we have seen the normal strain as change in length by original length. So, if you want to find out the change in length, you have to just multiply the epsilon xx with the original length. So, change in length of side due to deformation. In this case, when I say deformation, only normal strain is epsilon xx into delta x. So, multiply this epsilon xx the original length, which is delta x. So, that gives a change in length. What is the new length? Add this change in length the old length. So, length of side after deformation is the old length, the initial state length, and then whatever change that has happened, epsilon xx into delta x. In this diagram, it is shown that all the strains are positive, okay, because increase in length need not happen. Okay. Generally, this epsilon xx can be positive or negative, automatically it will reflect a decrease in length or increase in length. In this case, the diagram shows all lengths have increased. So, this is the new length, the old length plus the change in length gives a new length. Now, similarly, so that is what is shown here, delta x is taken as common out as common factor and shown as 1 plus epsilon x x into delta x, and similarly along the y direction, similarly along the z direction. Now, volume of element after deformation is just a product of all the lengths in the final state. Now, let us do some simplification. First, remember we are to relate to the displacement gradient, because of physical significance we introduced epsilon x x. Now, we will replace this epsilon x x with dou u x by dou x, similarly epsilon y y with dou u y by dou y, similarly in the s z direction. Now, let us take out delta x, delta y, delta z, they are common, and the first expression the term becomes 1 plus dou u x by dou x, similarly in the y direction and z direction. Now, we will have to multiply all this. Now, when we multiply, what we do is we neglect all the terms which are square, third, second order, third order, etc. Why do we do that? Remember, all our discussions are under the infinitesimal strain theory. Under that assumption, the normal strains are very small, let us say 10 power minus 6. Compared to that, when you square, it becomes 10 power minus 12, so which is negligible. So, we neglect all the higher order terms and only retain the first order terms, and that is why I have 1 plus only the first order derivatives dou u x by dou x, dou u y by dou y and dou u z by dou z. You will have terms which are products of these derivatives, in fact product of all the derivatives, all those are neglected. Second order terms onwards we have neglected, only the first order terms are retained. So, what is that we have found out? The volume of the element after deformation has been found out. Now, we can find out the expression for volumetric strain. Volumetric strain, how do you define? Fractional change in volume. What is fractional change in volume? Volume after deformation minus volume before deformation and divide by volume before deformation, analogous to our normal strain definition, new length minus old length divided by old length. Similarly, here volume after deformation minus volume before deformation divided by volume before deformation. Okay, now, let us express them in terms of our variables. We just now found out what is the volume after deformation, delta x, delta y, delta z into the bracket terms, and what is the volume before deformation, just delta x, delta y, delta z. Okay. So, now delta x, delta y, delta z cancels out, and then you will have one minus 1 here, and that cancels with 1, and what is remaining is the sum of these derivatives, dou u x by dou x, dou u y by dou y, dou u z by dou z, and which can be represented in terms of our gradient vector as divergence of the displacement field. Okay. So, once again we have come across these terms of just gradients earlier, and in terms of our displacement gradient tensor, those are the diagonal elements. When you sum up, you get a nice significance, physical significance, tells you the fractional change in volume. So, del dot u, the divergence of the displacement field, one way is look at as divergence of displacement field, other way is look at it as tells you the fractional change in volume. Okay. Now, when we started the derivation, we said there are only normal strains. What happens if you include shear strain? If shear strains are also considered, no contribution to change in volume, still you will get the same expression. The reason is they will only contribute to the higher order terms. Okay. We are not discussing that. If you include shear strains, meaning change in angle, the final result will still be same, the final result will be still be same, that is the fractional change in volume will still be same. Reason is you will have terms here, additional terms because of the change in angle, but all of them will be higher order terms only. Okay. That is why it will not contribute towards the final expression. Conclusion is that only normal strains contribute towards volume change within our infinitesimal strain theory. Within our assumption, if I have an object and if there is a change in angle, volume still remains same, but obviously if there is change in length, there is going to be change in volume. Okay. Conclusion is that only normal strains contribute towards volume change. So, what we have done here is introduced another strain, namely volumetric strain, and which is fractional change in volume, and derived an expression relating volumetric strain to the displacement gradients. They are nothing but the sum of the diagonal elements of the displacement gradient tensor. Okay.